Okay, so welcome to this AsiaGraphics webinar session 5. So this is the Peng Song from Singapore University of Technology and Design. So in this session, it's my great pleasure to have three speakers, Shiwen Fu, and Cng Lee, and Ray Lee. They will give research topic on machine learning for point cloud processing. So our first speaker is Shiwen Fu. He will give a talk on deep 3D sensing pipeline, feature learning, pre-processing, understanding, and applications. Shiwen Fu is currently a full professor at the Chinese University of Hong Kong. He served as the associate editor of IEEE Computer Graphics and Applications and Computer Graphics Forum, co-chair of SIGGRAPH Asia 2016 Technical Brief and Post Program, panel member in SIGGRAPH 2019 Doctoral Consortium and Program Committee members in various research conferences, including SIGGRAPH Asia Technical Brief, SIGGRAPH Asia Emerging Technology, IEEE Visualization, AAAI, CVPR, IEEE VR, VRST, Pacific Graphics, GMP, and so on. His recent research interests include point cloud processing, 3D vision, computational fabrication, user interaction, and data visualization. So, hi, Professor Fu. So now the floor is yours.
Yeah, thank you, Song Pa. Maybe let me share the screen first.
Yes. So let me start sharing.
Okay, can you see my screen?
Yes, I can see.
It seems the screen is still not broadcast yet, is it?
Really?
Oh, okay, you got it.
Yeah, so the floor is yours.
Okay, thank you. Thank you, Song Pa, for the introduction, and welcome everyone for attending my talk. Okay, in today's talk, I will focus on the 3D sensing pipeline, which starts from feature learnings, and ends with some downstream applications. And in fact, the three talks today are deeply connected. In my talk, I will focus on overviewing my research works on different parts of the 3D sensing pipeline. So in my part, I will mainly introduce the key ideas and our major results and skip the technical detail. Then in the next two talks by Professor Lee Xianji and also Dr. Retrieval Lee, they will give a deep dive into the technical details of their work in the 3D sensing pipeline. Okay, so let's get started. When we start a research project, we must start with a clear research goal. So what is the goal of the 3D sensing pipeline? Having said that, I mean that after we use various kinds of sensors to acquire data about our physical environment, no matter the environment is indoor or outdoor, in object level or in human level, what we may achieve, okay, with the acquired data is the key issues. Okay, essentially the end goal of 3D sensing is to extract certain 3D information or 3D structure out of our acquired data from the sensors, such that these high-level information can provide a 3D perception of the space so that we can further support or enrich various kinds of relevant downstream applications. Here, I show you some of the applications that my group has done, which includes real-time 3D object detections, 3D scene understanding, and recently, we also work on some projects with mechanical engineering researchers, and our goal is to enable the robots to have a 3D perception of the environments such that we can effectively pick small objects in a bin. Also, by sensing our hands and reconstructing screen-aligned 3D hand measures in real time, we can also support various lawful user interaction scenarios, particularly as so in this work. Our method, okay, our real-time method is able to enable the user to directly use bare hand to grab and manipulate virtual objects in AR environments, so that the phone you see here are actually virtual, but the hand here is actually real. Now, let me show you the 3D sensing pipeline. After we acquire the data from the 3D space, I think the very first step is feature learning. It is because most of the 3D sensing and 3D perception methods nowadays are based on deep neural networks. Then we need to preprocess the data, for example, to denoise the data, to upsample the data, or to consolidate the data. After that, we can try to process the data and extract high-level 3D structure or 3D information out of the data. For example, for the purpose of object localization and object segmentations to support, and then based on these kind of high-level information, we are able to support or enrich a wide variety of downstream applications. So let's look at each of these 4 components in the pipeline one by one. The first one is feature learning. For feature learning, I will share with you the following 3 research works, which is published in the recent 2 to 3 years. Nowadays, we all know that the quality of features are very important for promoting the performance of many methods, especially most methods nowadays are based on deep neural network. Following PointNet, an early work that we did is PointWeb, in which we try to enrich or enhance the point features by densely connecting each point with every single label in a local neighborhood, such that we can promote the message passing or information exchange between points in local neighborhoods. And then the network can thus be able to learn to have better feature representation for the local neighborhood. In PointWeb, we also developed several lawful modules to enhance the point features interactions and demonstrate the capability of our method on improving the performance of various tasks, such as point clouds, 3D segmentation, and also 3D object classification. For detail, please look at our paper. Another aspect that we have tried for enhancing the point feature learning relates to the data augmentation. Unlike existing data augmentation techniques, which are often based on manual design or based on some heuristics, we design point augments. It is the first approach that explores how we may automatically learn to augment point cloud samples to enrich the data samples, diversity of the data sample. Okay, essentially, point augment is an automatic augmentation framework in which we adopt adversary learning to jointly optimize an augmented network, okay, which is the one I showed here. And then on the other hand, we also have another network, which is the task networks. And particularly in our method, we actually take the feedback or the loss values from the task network to train and improve the augmented network such that it can learn to augment and produce point cloud samples that better fits the task. Okay, and then in this point augmentation function, I want to highlight that this function is learnable with a strip level transformation and also a point level displacement for highly robustness. Lastly, we also demonstrate that by using our method, we can incorporate our point augment into different kinds of classification networks, and then we can show that by doing so, we can improve the model performance of many methods. Again, for more details, you can refer to the paper. Lastly, we explore rotation invariant point features. The motivation behind this work is that most existing works simply take 3D point cloud as input for extracting point features from the point clouds. Hence, they have good performance mainly when the test objects have the same or similar orientation as the objects in the training set, which corresponding to the blue bars here in the blue bar here in the plots. Because for the blue bar, it means that we train on the C axis and then test on also the C orientations. In other words, when we try to use this kind of trained networks on different kinds of for objects with different kinds of arbitrary orientation, they will have more poor generalization, which corresponding to the orange bars here, which means that we train on the C-axis orientation and then try to test the trained network on objects of arbitrary orientation. Okay, to overcome this issue, we design a lawful representation shown on the right-hand side, which is purely rotation invariant, and our representation encodes not only local structure, local shape, local information, but also global information, as well as we design the representation to be more robust to noise as well as outliers. As this work will be presented in the second talk by Cng Lee, please stay tuned and find more detail in the second talk. Okay, let's go back to the pipeline. After we extracted the point features, okay, to improve the performance and also the robustness of the overall 3D sensing pipeline or the 3D perception tasks or application in the end, another step that we often need is to pre-process the data. And in this pre-processing part, due to the amount of time I have, I will mainly focus on briefly introducing my works on point cloud upsampling and also point cloud consolidation. So let's start with point cloud upsampling, for which my group has developed a series of works on it. Briefly speaking, the goal of point cloud upsampling is that given a sparse and noisy input point cloud, we aim to produce a dense and clean output point cloud that describes the same underlying object surface. The general approach for point cloud upsampling with deep neural network is that after we extract the features for each point in the point cloud, input point cloud, then we will expand the amount of features, which means we produce more point features in the same feature space, so that we can later reconstruct one point coordinate from each expanded point features and then produce more points in the 3D object space. Okay, so in the first work we did, which is the PULETS, it is the first deep neural network model that we try to upsampling 3D point cloud. Compare with the recent work on 3D point cloud upsampling nowadays, of course, the idea in this work is rather simple. In this work, basically, our idea is that we first learn multi-level features per point and then adopt a multi-branch convolution units to expand the point features implicitly in the 3D in the feature space rather than in the physical 3D space, because in doing so we can expand the feature more easily, than in the physical space. Particularly, we want to upsample the points in a patch level, which is easier to learn with a reconstruction loss to encourage the upsampled points to remain on the underlying surface, and also we develop another loss, which is the repulsion loss. So here, in which we try to push the points further away from one another in the final upsampled results. Overall, I think the major ideas in this work is that we have the overall framework that allows us to upsample point clouds using deep neural networks, and then the idea of expanding the point features in the feature space rather than in the physical 3D space. Okay, looking at the 3D reconstructed results. So on the right-hand side, based on PULETS, on the chair corner, we can see that the PULETS actually can easily over smooth the edges in the upsampled point clouds. This result actually motivates us to further explore whether we can upsampling points at the same time considering the sharp edges and also try to respect the sharp edges on the underlying surface. Having said that, we aim to further preserve the sharp edges by trying, our idea is to try to generate more points, along the sharp edges. So how this can be done? In this work, we developed something we call the EC-LET. EC means not easy, it means edge consolidation. So to approach the problem, we first create a regression loss, in which in this loss or regression component, in which we try to recover the 3D coordinate. And then after we recover the 3D coordinate, we try to estimate the distances between each of the 3D coordinate to the annotated edges, in the resultant point clouds or in the generated point cloud. And then in the lab work, we try to measure this distance. If this distance is small, we try to push the points towards the edges. Which means that we try to encourage the network to generate more points on the sharp edges in each patch that is being trained. So using this method, we can further formulate an edge-aware loss, John loss, to directly minimize such distances. And by this means, we can further, based on the annotation, to try to push the points more close to the edges. And in doing so, we found that we are able to train the network to identify points that are near edges and also encourage these points to be closer, not just to the underlying surface, but also close to those annotated edges. In this way, our network is able to upsample more points that are closer to the edges. But of course, one deficiency in this approach is that it requires some annotation. So that's why some recent work by some other research group try to overcome this issue in a more unsupervised manner. Okay, but still you can see if you compare the result of this work, our ECLET with PULET, you can see the result is greatly improved. And our result is our method is able to help produce more better 3D reconstruction that can respect the edges. Also, we try to apply our ECLET on both real scan data as well as synthetic data in order to demonstrate the capability of this work. Okay, I recall that when I was a graduate student many years ago, one of my teachers in those old days reminds us that research basically is search again. Okay, it means that we have to try to identify issues or shortcomings in the existing work and then try to overcome the issues. So that's why our third paper in this series on point cloud upsampling is this PU gun, which starts with the observation that the upsampling point clouds, as you can see here, okay, on the right hand side, usually have very poor point distribution pattern. Okay, so that's why we can see some of the points are actually quite close to each other. Okay, so they cannot effectively or efficiently describe or represent the underlying surface. Hence, after we finished PULET and also ECLET, I challenged my PhD student on whether they can design a neural networks that can produce point distributions that are more uniform, following something we call people call it the blue noise sampling pattern. Okay, after that, we actually invented the uniform laws and also the PU gun framework, so here, which can help us to produce much better point distribution in terms of uniformity. You may see that our results show on the right hand side, which is more uniform than the one shown by the previous work. Okay, since the third talk today by Cng Lee will be covering this PU gun, okay, I will skip the technical detail, so please stay tuned and then look at his talk later. Last year, we further revisited the point cloud upsampling task again. And our new concept observation here is that the task is in fact quite complex since it involves multiple objectives by nature. It is because when we upsampling a point cloud, we not only want the upsampled point cloud to be close to the underlying surface, we also want the upsampling point cloud to have good point good distribution, point distribution uniformity in terms of uniformity, etc., etc. Since it is quite complex, okay, to have a single network to simultaneously consider multiple objectives. So our new idea here is that we propose something we call the DPU. D means disentangle, okay, to disentangle the complex point cloud upsampling task by formulating two cascaded subnetworks, which includes a dense generator and a spatial refiner. Okay, and here you can see extensive results, okay, quantitative and quantitative results on both synthetic and real scan data demonstrate the goodness of our method over the previous work, which is a PU gun and so on and so forth. PU gun and PULET and so on and so forth. Again, this work will be presented in more details in the third talk today. So that's why I will skip the detail. Please stay tuned. Okay, another work that we did on 3D data preprocessing is a mesh denoising work, in which we design a deep neural networks to learn to filter normal vectors on 3D meshes without requiring explicit surface information to aim a better 3D reconstruction. Due to time limit, I will skip this talk, but if you're interested in this work, you may find more technical detail in the research paper. Okay, so after we extracted the point features and also pre-processed the data, we are ready for the next step, which is 3D perception or 3D understanding or 3D scene understanding, in which we try to further infer some high-level 3D information of the environment surrounding us. And here I will introduce some works on 3D object detection, 3D semantic and instance segmentation, and also label efficient or annotation efficient 3D segmentation. And lastly, I will also introduce my very recent work on 3D to 2D distillation method for scene parsing. So, okay, let's go to the first one, which is 3D object detection. In this, in the research literature, research on 3D object detection mainly focus on autonomous driving scenario, which means the goal is to detect 3D bounding boxes that enclose or locate the objects such as cars, bicycle, pedestrian in the input point cloud. To meet the sheer practical needs, the detection should not only be accurate in terms of FH precision, but also be fast in terms of the network inference speed as shown in the plot on the right-hand side. We can see that more recent work are focusing on both speed and accuracy nowadays. And if you look at the shaded area in this plot, you can also see that the shaded area actually help to mark the methods that can run in real time. And in our very first work, which is this called CIA SSD, SSD stands for Single Stage Object Detector. Okay, we aim for both high speed and also high precision. So in this work, we first develop and also design a lightweight module, okay, to help us to extract feature. This module is called the Spatial Semantic Feature Aggregation Module, to adaptively fuse high-level abstract semantic information and also low-level spatial features. Particularly in this work, we try to align the two modules, okay, because there are two modules, there are two issues when we do object detection. One issue is that we want to locate the object, which is the object localization, and then the other thing is class classification. We want to classify the object, is it what kind of objects? So that's why these two tasks usually may not align well. So that's why in this work, we also develop an IOU-aware confidence rectification module to help us to further improve the accuracy by means of aligning this. Okay. Further, we also formulate some distant variant IOU weighted NMS to try to improve the result by removing the redundant predictions, bounding box prediction. For details, please look at the paper. Okay, and then another follow work, which is a very recent one that we presented in CVPR just a few months ago, is that it is called the SE-SSD, in which our idea is to improve the performance without making a more complicated networks. Okay, our idea is to create something we call something people call a self-ensembled frameworks. So in this framework, we will take advantages of the soft and hard target. Soft targets means something easy. Okay, it means the original point cloud. So on the left hand side, and on the other hand, we can use some kind of data augmentation on the same input point cloud, and then produce some augmented inputs. Okay, for the networks. Especially here, you can see we have two networks. One is the teacher SSD, the teacher single stage detector, and then the other one is the student single stage detector. For the teacher's detector, we use the more easy more easy soft targets, and then for the student SSD, we use the more challenging hard targets. And then during this self-ensembling framework, we basically design some consistency laws to make sure the final prediction is consistent, even though those hard targets is created after some data augmentation. So by this means, we can enrich the teacher SSD, okay, by using the student SSD knowledge, okay. So the good thing about this approach is that the teacher SSD actually has the same structure as the SSD, and both of them we have the same structure as the module, the feature extraction module that I present you in the previous work. So that's why using this approach without increasing the network complexity, we can improve the network parameter so that the network is able to produce even higher quality predictions than the previous work. Okay, and the good thing about this is very clear. So that's why it improved over the previous work we have. And then at the same time, because the network is a lot more complex than the previous one, we can also enjoy a very fast inference speed. And basically, you can say this kind of thing is based on knowledge distillation approaches. So that's why for detail, because of time, okay, for detail, you may also look at the paper. Okay, I guess I have to be faster. Okay, so let's move to another 3D understanding task, which is the 3D semantic segmentation. So what exactly is 3D semantic segmentation? It means that given a point cloud, we want to segment it into objects and also identify what kinds of object it is. For example, walls, chair, tables, a refrigerator, and so on and so forth. To do so, we have to design and train a deep neural network to predict a class label for each point in the 3D point cloud. A class label means the type of the object that the points belongs to. And in this work, our key idea is that we don't just predict a label for each point. We also predict a label for each edge. So what exactly is an edge? Actually, in this work, we try to connect points that are close to each other by an edge, and then we try to predict whether these 2 points have the same label, have the same class label. So by doing this, we can hierarchically create a graph over the structure and then try to produce something we call an edge loss, formulate an edge loss to try to encourage more information exchange in the graph, okay, to encourage the network to learn more results, to produce that results that is more consistent between the adjacent points. Okay, so let's go faster, I guess. We will further work on another work, which is on 3D instant segmentation. 3D instant segmentation is more than 3D schematic segmentation, because for instant segmentation, we have to predict not only a class label for each point, but also an instant label or instant ID for each point in the input point cloud, which means that we have to further separate the objects into individual objects. So our key idea here is a point clustering process. Okay, we try to incorporate a point clustering process in the middle of an end-to-end network, which is trainable, and then we call this one a point group, as so here. And first, basically, after we extract per point features, we try to create, to predict 2 branches. One is the semantic branches to predict the semantic label for each point, and then for each point, we also predict an offsets, vector, to try to move each point towards the centroid of the objects. So by doing so, we can create 2 point cloud. One is P. P means the original point cloud, and then the other one is Q. Q is created by shifting P, with the offset vector for each point. So that's why you can see in Q, the points are more concentrated near the object center. So by doing so, we can have 2 point set, which is the P and Q, and then we create another networks based on this P and Q to predict the object proposal or the clustering proposal using the scorelet. By doing so, we actually can take advantages of both P and Q, and then in order to produce a more accurate instant segmentation. So that's why from this result, you can see that by using both P and Q, we are able to create a better mean AP, mean FH precision than using P or Q alone. And furthermore, the good thing about doing so is that we also try this method, on both ScanNet V2 and also the SVDIS dataset. And point group, this method actually can produce very good performance compared with the formal best solution in terms of mean AP, as so here. Then the next thing I want to introduce is label efficiency. So for 3D schematic segmentations, most work actually nowadays just use assume fully annotated point cloud data. In this work, we actually suggest that can we use both labeled point cloud and unlabeled point cloud simultaneously to train our segmentation network in such a way that it can learn from both labeled data as well as unlabeled data. Since I don't have enough time, I think I will skip the technical detail. I hope you roughly understand the main goal of this work. Another approach that we have tried to reduce or to the annotation burden or to try to make the label efficiency higher is that we try to allow us not to fully annotate the entire point cloud, but rather just to provide 1 point for each object in the point cloud, as so here. So here we show that this kind of work is that by using even just 1 point cloud, 1 point for each object, we are able to train using this self-training model to train the entire network in order to produce a result that is quite natural, by means of just a few iterations in this self-training process. So due to time limit, I guess I have to be even faster. The last word I want to put in more time because I think this word is quite interesting. Because in this word, we try to solve the problem that if we have point cloud data, can we use the point cloud data only during training to improve the 2D image segmentation network? Which means that can we train the 2D segmentation network, which is this 2D CNN I saw here, okay, to improve it to produce better 2D segmentation result. So the challenge here is that we can have 3D point cloud data only during the training process, but lots during the testing process. So how can we achieve this? So our idea is that during the training, we try to train the 2D CNN networks to produce something we call the simulated 3D features. And then we use a consistency loss between these simulated 3D features and the 3D feature extracted from a pre-trained 3D segmentation network. So by doing so, the good thing is that if we can train the 2D networks to produce these kind of simulated features that are similar, okay, to the 3D features from the 3D CNN, then during the testing, we do not need point cloud data anymore. We can get rid of the top pass and only use the 2D CNN to produce these kind of simulated 3D features. And then during the testing, we can simply use these simulated 3D features to improve the performance of the 2D segmentation. And as so on the right result presented in this slide, we can see that our 3D to 2D distillation approach actually can improve the overall performance, okay, of our result. And we can actually improve the performance over other methods based on some generic knowledge distillation or some depth-based method. Okay, and finally, I think I have to go faster and then just quickly overview this kind of different kinds of downstream application that my group has done. Okay, here I want to show you some results on the following applications. The first two basically are related to geometry learning and 3D shape generation and manipulation. And the third one is on robotics. And then the last two are on some augmented reality. Okay, for the first word, I think the second talk we talk about it, so I will skip it, but just talk about the interesting part in this word. In this part, I think the most interesting word, the most interesting thing about this word is that we designed an unsupervised network, which means we don't need to have any label. Okay, we don't need to label where are the distinctive region, but our network can, based on some clustering method, it can detect and then find out what are the distinctive regions on different objects compared to other objects. As you can see in this result, we can highlight the engines on the aeroplane and also highlight different parts on the 3D shapes that distinguish it from other objects. And then in the second word, which is quite recent in a few months ago, presented in SIGGRAPH 2021, in this word, we try to create a generated network, okay, to generate the network with some code. And then the interesting thing about this word is that we have a code that is attached to different points on these Pia objects, which is a sphere Pia. Then we, based on this information, something related to this entanglement, okay, we can allow some kinds of manipulation. Okay, for example, multi-shape parts manipulations or composition, and also part-wise interpolation and also shape interpolation. Okay, please stay tuned. I think in the third talk today, Roy Kwai Lee will also present more detail in this work. And then in the third word, we actually try to practice our 3D sensing pipeline, okay, on different kinds of robotic scenario, for example, beam picking and also box gripping, as shown here. Okay. And using this method, we found that we can really enable the robot to locate to segment out the point cloud as well as the image space for the objects. And then after that, we can also enable the robot's arm to more efficiently pick up individual objects as shown in these demonstration videos. Okay, and then the last two is related to AR. Okay, basically we have done two works on AR based on 3D sensing. The first one is that we try to sense where are the building plane and also where are the fault lines. Okay, and then based on building plane and fault line, we try to allow some AR content to be more effectively overlay on the building plane, which is fault level line aware or building plane aligned, so that we can produce this kind of AR applications. Okay, and then another word which is quite recent in ICCV 2021 is that we try to support and enrich direct hand interactions. Okay, and then in this work, the most interesting part, I think, is that we try to align the hand, okay, the real hand together with the virtual reconstructed 3D hand mesh, not just in the real space, but also in the finger level. So by doing so, we found that we can more accurately produce the hand meshes, and then this kind of hand meshes can be done in real time by our methods, generated in real time by our method, so that we can take it to enable this kind of direct hand interaction, as you can show here. Okay, which means that by doing so, based on our method, we can enable the user to use bare hand to directly grab and also manipulate different kinds of virtual objects. Okay, as you can see here in this video in an egocentric view. Okay, so I think time is short. Okay, I'm near the end of my part. Okay, and actually I guess I'm too ambitious to try to overview almost 20 papers already. Okay, so I hope you enjoy the talk, even though I do it very quick. Okay, but I didn't go. Apologize that I didn't go very deep into the technical detail. Okay, but still, when you see so many work that I have done, I really want to say that to make all this work happen, okay, I need the support, okay, from my research student and also the research staff. And I'm very grateful, okay, to have many talented research students and also postdoc in my team, as well as the student helpers and collaborators who helped me a lot in doing all this research work. Besides, I also would like to thank the various funding agency and research center for supporting my research work. Okay, I think this is the end of my part. Okay, let me unshare the screen and pass the time to Song Pang, okay, for introducing Cng Lee, okay.
Okay, thank you, Philip, for the inspiring talk. I think I have a number of questions to ask, but I think if any audience have questions, you can post your question in the YouTube or the Huya live chat box, and the speakers will address them at the end of the 3 talks. So now let me introduce the speaker of the second talk, which is Cng Lee. So his talk title is Robust 3D-point cloud analysis via deep learning approaches. Cng Lee is recently joined the School of Computer Science and Technology, Huadong University of Science and Technology as an associate professor. Prior to that, she was a postdoctoral fellow at the Chinese University of Hong Kong and the Hong Kong Center for Logistic Robotics. She received a PhD degree in computer science from the CUHK in 2020. Her research interests are in 3D vision and computer graphics, with a recent focus on developing machine learning methods to advance the processing, analysis, and understanding of 3D-point cloud data. So, Cng Lee, now the floor is yours. So let me.
Okay, thank you.
Yeah.
Can you see my screen?
Yes.
Okay, thanks for the introduction. Today, I would like to share our works that focus on robust 3D point cloud analysis via deep learning approaches. In this talk, I will first give a brief introduction to the background of deep point cloud analysis, and then introduce our 2 works, rotation invariant point cloud analysis and unsupervised distinctive region detection, then followed by the conclusion and future work. As Philip has introduced, in recent years, due to the popularity of various depth scanning devices, the amount of accessible 3D data has increased by several orders of magnitude. So until now, there are many public 3D benchmark datasets. For example, ShipNet and ModelNet are 2 commonly used datasets that provide single isolated objects, while Kitty and ScanNet are 2 large-scale scene-based datasets. Of course, there are still many other datasets, and I won't list them all here. So this significant growth of available 3D datasets pushes us to redefine the problem of point cloud analysis from the perspective of big 3D data. On the other hand, we all know that deep neural networks have been applied to many fields with great success, such as 2D computer vision, natural language processing, or even AR or VR. So motivated by the above 2 points, in recent years, there is a new trend of analyzing 3D point clouds using deep neural networks. However, we cannot directly apply these deep neural networks that are developed for 2D images to 3D point clouds. Next, I will introduce several challenges. The first one is that point cloud data is unstructured. They are not placed on a regular grid. For each point, its distance to the neighboring points is not always fixed. So this is quite different from 2D images. The second challenge is that a point cloud is a set of points, so they are unordered. As a set, the order in which the points are stored doesn't change the object or the scene it represented. So due to the 2 challenges, we cannot directly apply CNN to 3D point clouds. Also, the third challenge is that the real scanned points are often not evenly distributed across different regions. For example, some region may be very dense, while others may be very sparse. So this is the non-uniform property. Also, an object in 3D space can be rotated arbitrarily. No matter how this object is rotated, it is still this object itself. So how to ensure that the extracted features are not sensitive to the object orientation is also a challenge. Of course, we all know that compared with 2D images, 3D data is harder to acquire and label. So how to maintain the stability of our algorithm and low training resources is also worth exploring. For the first 2 challenges, there are a lot of works that try to address, like PointNet, DGCN, or PointCN, etc. So I won't go into the details of addressing the 2 challenges. For the non-uniform issue, our next speaker will Ruihui will mention a bit. So in my talk, I will mainly focus on the 2 challenges and introduce our solutions. Now let's move to our first work, rotation invariant point cloud analysis. It was published in TVCG this year. Let me first explain what is rotation invariance. For a rotation invariant method, the features extracted by the deep neural network should remain the same, given an input at arbitrary orientation. For example, for the same point cloud with 3 different orientations, the extracted features should be the same because they all represent the same object. However, most existing point deep neural networks are rotation variants, meaning that the extracted features are very sensitive to the object orientations. So to achieve rotation invariance, a common solution is that we can apply rotation augmentation to the training data. However, if we apply the aggressive rotation augmentation around a random axis, the network performance may be harmed because existing networks don't have strong capacity to learn effective features from such unstable inputs. So existing works consider only the rotation augmentation around the gravity axis, but such limited augmentation cannot generalize well to the unseen angles. Here I will show you a figure. Here the blue bar indicates the classification accuracy when we train and test the object with rotation about the gravity axis. We can see that the classification accuracy is very high. The orange bar here shows the classification accuracy when we train with the gravity axis, but test with arbitrary orientations. And we can see that there is a significant performance drop. So it means although we apply the rotation augmentation during training, these networks are still sensitive to the orientations. So to address this, in our work, we argue that a framework is rotation invariant if both network input and network operations are rotation invariant. So we propose a purely rotation invariant network input and a rotation invariant network architecture. Now let's talk about the first point, how to design a purely rotation invariant network input. It is not difficult to answer this question. We can simply use relative attributes. For example, we can use this relative angles or relative distances to replace point coordinates as network inputs. These relative attributes will not change no matter how we rotate this point cloud. But we should know that compared with the original 3D coordinates, this simple relative geometric information will cause a lot of information loss. Because given only these simple relative attributes, we cannot know how the original points are distributed in 3D space. So when we design the rotation invariant network input based on these relative attributes, we should first try our best to minimize the information loss by capturing both local and global information. And the second thing we should pay attention to is that when we design the rotation invariant network input, it should be tolerant to noise, because in real application, it is unavoidable that the scanned 3D point clouds may be noisy. As for designing the rotation invariant network input, there are also two aspects that we should pay attention to. First, the network cannot involve any rotation variant elements or operations. For example, some attention module may be designed based on the point coordinates. So we cannot use this kind of operation. Second, considering that the relative information is too local, so when we design our network, we should pay special attention to introduce more global information into the embedded point features. Now, keeping these points in mind, let's first look at our rotation invariant representations. For each point Pi, instead of feeding its 3D coordinates into the network, we extract its global rotation invariant representation and local rotation invariant representation. This global representation can capture Pi's location relative to the whole object and also to its local neighborhood, while the local representation can capture the local structure around Pi. The local structure here means the spatial information between Pi and its neighbor point Pij. So in our global representation, we designed 5 pieces. So as shown in this subfigure, these green symbols are the global representations, and we can see that they are all based on relative angles or relative distances. So they are purely rotation invariant. So here I want to mention that Mi, the point Mi here means the center of the local neighbors. A common choice of calculating the center is the centroid. We can directly calculate the averaged point coordinates over all the neighboring points as the center. However, in our implementation, we use the geometric meaning because this geometric meaning is more robust against noise. In the local representation, there are totally 7 pieces. So the red symbols indicate our local representations. Here, I want to emphasize that our local representation is ambiguity-free. Ambiguity-free here means that using the 7 pieces and the position of Pi, we can uniquely determine the position of Pij. So the local region is ambiguity-free. It means that different local regions have their unique local representations. Otherwise, it may cause ambiguity in the network training. This is our designed network architecture. We design a deep hierarchical network with totally 3 layers. These green boxes indicate the point coordinates. We don't feed them into the convolution module. Instead, we extract its rotation invariant representations as these yellow boxes, and then feed the rotation invariant representations into our designed region relation convolution module to extract the rotation invariant features. So here shows the detailed architecture of the region relation convolution. The key insight of this module is that besides the commonly used shared MLP and max pooling, we further regress a weight. This weight is regressed from the global relation matrix. This matrix contains the angles and distances between all point pairs. So this weight can reveal a certain of global relations between all the points. So in this way, when we introduce the weight into the feature embedding process, the extracted features will encode not only local information, but also a certain of non-local relations. So once we obtain the embedded rotation invariant code word, we can do various applications, including shape classification, object part segmentation, and shape retrieval. Here shows the shape classification result. We can see that for our method, there is no performance drop, even test on the arbitrary orientations. This is the visual comparison of the object part segmentation. Our method is the results produced by our method are the closest to the ground truth. This is the shape retrieval result. Our method achieves the best average score with a significant margin. So next, let's move to our second contribution, unsupervised distinctive region detection. This work was published in TOG last year. As I mentioned earlier, exploring unsupervised learning is particularly necessary because acquiring and labeling, especially on 3D data, is very time-consuming. Also, without supervision, the network can learn more possibilities freely. Next, let me give the definition of shape distinction. Formally, the distinction of a surface region in an object is defined as how useful the region is for distinguishing the object from others of different types. This concept is hard to understand, so next I will show you an example for you to better understand this definition. Now look at here. There is a spoon and a fork. Now if I hide the top region and only show you the bottom region, can you still tell which is the spoon and which is the fork? Obviously, the answer is no. Now, if I hide the bottom region and only show you the top region, I think all of you can easily distinguish the spoon and the fork. So in this example, we see that the top region is distinctive because the two regions can help us to distinguish the two different objects. So now let's see another example. Here is an ordinary spoon and a cartoon spoon. So how to distinguish them? In this case, we should look at the handle part. So we see that given the two kinds of spoons, the handle regions are now distinctive. So from the two examples, we can draw two conclusions. First, the distinctive regions of a shape should be common and unique in its own type, compared with shapes of other types. Second, the distinctiveness of a region is quantified relative to a given set of 3D shapes. This means that for the same region, its distinctiveness may change according to different given sets. So after understanding the definition of shape distinction, You may ask, why do we need to detect the distinctive regions? Now I present several typical applications. First, we can employ the distinctive regions to perform the fine-grained shape retrieval. For example, given this region as distinctive, we can retrieve chairs with similar substructures. Second, we can do the distinctiveness guided point cloud sampling. As shown here, when we do the point cloud sampling, we can preserve more points on these distinctive regions. So in this way, even with fewer points, we can easily tell that the engine of this airplane is located on the tail part. Third, we can do the best view selection. We can show these views with the maximized distinctiveness because these views commonly contain more useful information. Actually, we are not the first to explore shape distinction. In 2007, this work first introduced the concept of shape distinction and designed a traditional method to detect distinctive regions. About 3 years ago, a weakly supervised deep learning method was proposed. But in our work, to avoid the annotation efforts, we propose an unsupervised method. From the definition of distinction, we could know that the essence of distinctive detection is to classify objects. So in our work, we transform the problem of distinctive detection to the problem of shape classification. Also considering that analyzing point clouds is much easier than analyzing a 3D shape or a mesh. So in our work, we sample points on each shape as the network inputs. So given a set of unlabeled point clouds, we design our network to extract per point features and per shape features. The per point features will be later used to extract the per point distinctiveness, while the per shape features will be used to conduct the unsupervised shape clustering. So the key contribution of this work is the unsupervised joint loss function. It contains two loss terms, clustering-based non-parametric softmax loss and the advanced contrastive loss. This clustering loss can drive the network to cluster objects in an unsupervised manner, and the contrastive loss can help stabilize and enhance the network learning. So next, let's go to the details of each loss term. We first review the commonly used supervised softmax classifier. The probability of the jth object being recognized as the Q's class is this equation. The WK here means the class prototype of the K's class. It is learned from the provided class labels. So if no class labels are given, this equation cannot be used. However, an observation found that when a network has successfully converged, the class prototype W is usually consistent with the average of all the feature vectors belonging to the same class. So motivated by this, we formulated this equation. We use the G bar to replace the WK here. The G bar means the average feature vector over all the per shape features within the same cluster. It means that during training, we use a clustering algorithm to cluster all the per shape features into different clusters. And then within the same cluster, we calculate the average feature vector as the G bar to replace WK. So in this way, the cluster loss is formulated by minimizing the negative log likelihood of this probability. However, it is inevitable that some training samples may be wrongly clustered. So relying only on this loss may not be sufficient to drive the network learning. So to stabilize and enhance the network training, we further formulate this adapted contrastive loss. Instead of feeding only one sample, we input a triplet, which consists of an anchor, a positive sample, and a negative sample. The anchor and the positive sample should be in the same cluster, but the anchor and the negative sample should be in different cluster. And then we use this equation to encourage the anchor and the positive sample to be close to each other while pushing away the anchor and the negative sample. So finally, the per point distinctiveness is obtained by taking the maximum value of each row in the per point features. Since our final goal is to detect a distinctive region on a 3D shape, so we further project the per point distinctiveness on the point cloud back to the original shape for visualization. Here shows some examples of the detected distinctive regions. Red color means that these regions are more distinctive. For example, for this person shape, our network found that the head, hands, and feet are more distinctive, while the body part is not distinctive. Also, we explore the effect of using different training sets. So in this experiment, we prepared 2 kinds of training data sets. In the first training data set, we collected some 4-engine airplanes and 2-engine airplanes. And then we use this kind of data set to train our network and then test the network on the 4-engine airplanes. And we can find that our network detects all the 4 engines as distinctive. On the other hand, in the second training data set, we collected some 4-engine airplanes and 2-engine airplanes. And in this case, our network detects only the outer 2 engines as distinctive. So this experiment shows that our method can indeed find and highlight the difference between different classes. Next, I will show you some typical applications. The first one is ship retrieval. In the ship retrieval, generally, we use the per ship global feature to calculate the ship similarity. However, to facilitate the fine-grained intra-class ship retrieval, we can select only the more distinctive per point features and average over them as the global feature to calculate the ship similarity. So here shows the results. Clearly, with the help of our detected distinctive region and the retrieved ships are more similar to the queries. For example, this query chair has 4 fixed legs, and all the retrieved chairs have similar substructures. The second application is the distinctiveness guided sampling. Different from the traditional Poisson disk sampling, we can sample more points. We can sample points by preserving more points on the distinctive regions. So from the plots, we can see that even the point number is very small. We can easily tell that this airplane has totally 4 engines. The last application is the wheel selection in 3D scenes. We here define the best views in a 3D scene as those with the maximized distinctiveness. So compared with these worst views, our selected best views can deliver more useful information. So that's all of our 2 works. Here comes to the final part, conclusion and future work. In today's talk, I introduced our 2 works, rotation invariant point cloud analysis and unsupervised distinctive region detection. However, the field of deep point cloud analysis is still at its infant stage, and more efforts can be done to progress forward. So here I briefly present some future works. The first one is how to extend existing works from single object analysis to large-scale 3D scenes. Second, we can also explore the few-shot or unsupervised learning. Also, we can also explore the domain adaptation or transport learning, because the data distribution scanned by different devices may be quite different. So finally, let me take this chance to thank my two supervisors and all my collaborators. They provide me strong support in my previous works. So that's all of my sharing. We have shared our codes. Welcome to have a try. Thank you.
Okay, thank you, Xianzhi, for the very nice talk. So now let's move to the third speaker. So let me share my screen. Okay, our third speaker is Ruihui Li, and he will give a talk on 3D geometry learning from unsampling to generation. So Ruihui Li is currently a postdoctoral fellow at the Chinese University of Hong Kong, and will soon join Hunan University as an associate professor. Before that, he received his PhD degree in the Department of Computer Science and Engineering from CUHK in June 2021. His research interests are in deep geometry learning, generative modeling, 3D vision, and computer graphics. And he is particularly interested in 3D reconstruction and generation with high controllability. Most of his publications are presented as top-tier journals and conferences such as SIGGRAPH, TVCG, CVPR, and RCCV. Okay, Ruihui Li, now the floor is yours.
Okay, I will share my screen. Okay, let's start. Okay, thank you. I'm glad here to present my recent works on 3D geometry learning. Today I may talk about the upsampling and the generation. Point cloud analysis. Actually, for 3D geometry, actually we have different kinds of representation. But here I mainly focus on the point cloud. The point cloud analysis through the deep learning is mostly start from the point net, and also after that, a lot of following works are proposed for different applications such as classification, segmentation, and also detection. Generally, deep neural network often rely on large amount of trained data and high quality annotation. Actually, this question is similar for no matter for the 2D image and 3D point clouds. However, point cloud produced by the 3D scanning often contain different kinds of artifacts such as the noisy, spirality. Therefore, it's more desirable to enhance the raw data before we can effectively use it for general analysis. Also, the 3D annotation process actually is much more complex than that in 2D images. Thus, the set of the 3D dataset are much smaller and also with limited diversity. So I want to, instead of manually collecting different data, it's more desirable to enlarge the 3D dataset automatically. In my research work, I mainly focus on these two issues. We can enhance the raw data that's specified for the 3D perception. Here, for example, given the sparse input, we can upsample it to get a dense output, and thus facilitating the surface reconstruction. On the other hand, we can also try to learn to generate some gross and new objects to enlarge the original dataset automatically. Next, I will talk about the main idea of these works. First is point cloud upsampling. Point cloud produced by the 3D scanning are often sparse, non-uniform, and noisy. Just look at these examples. Although we have tons of scanned points, but only a few points are allocated to the meaningful objects, such as the pedestrian and the cars. Given such a sparse and noisy input, point cloud upsampling is aimed to generate a dense output, which can provide a more faithful representation of underlying surface. Traditionally, we may use some optimization-based method, but this optimization-based method often rely on some shape attribution, such as smooth surface and accurate normal. Therefore, the performance and the generalization of this method are often limited. In contrast, learning-based methods often achieve a better result by only taking the raw point clouds. Here is a general pipeline for the point cloud upsampling. We first get the feature extracting from the input point clouds, and after that, we expand the feature, and after that, we regress the output coordinate. Before we talk about our method, we first elaborate on task formulation, particularly about how to prepare the training data in those learning-based methods. For each model, we crop a lot of small patches and using the Poisson disk to generate a uniform point set as our target output. And when during the training, we conduct a random sampling from the ground truth to get our sparse input to fit into the network. This formulation actually makes the upsampling method often have a good generalization. Here is the visual preview. Given the sparse input, the previous work also can actually be successful to produce more points. But compared to the previous work, the result of our method is called PUGAN is more uniform and clean. First, I will talk about the motivation. Given the sparse and the non-uniform input, the previous work just tend to generate more points around the original input, such that the output is non-uniform. But here, I want to emphasize on the uniformity. Look at the two disks on the right hand. Even with the same number of points, but the uniform distribution given provide a better perception and also better for the downstream tasks. In our work, our contributions focus on improving the uniformity of the upsampled result. One of the main contributions is a uniform metric. It's inspiring by the mosaic tyranny, and inspired by that, we formulate a uniform loss, try to give in explicit regularization. And here is a visual example. Given the same number of points, our uniform metric is sensible to the point distributions. Actually, this uniform metric is also applied for other tasks such as point cloud completion. Another contribution is GAN-based framework design. Actually, we designed the first GAN-based method for the upsampling. Here is the overview of the proposed network. We also provide some design some several modules to enhance the feature learning. But here, if we want to get more detail about the uniform metric and the framework, you please refer our paper. For this work, we also provide a new data set, and this data is rarely used in the upsampling tasks. Here is the visual comparison. We provide the upsampling result and also the corresponding mesh reconstruction result. As we can see that our PUGAN can produce more fine-grained detail, such as the elephant nose and the tiger's tails. We also provide a quantitative comparison. Our network actually achieve better performance for all the evaluation metrics. Particularly for the uniformity, our method is also achieved better, indicates that the point generated by our method are much more uniform. Here we also first conduct the upsampling on the real scanned KT dataset. It indicates that our model can generalize directly to the real scanned data without additional training. There is also another research demonstrates that our upsampled result can helpful for the 3D detection. This framework is also contains some limitation. First, it can hard to train due to the GAN framework, and also it may introduce some extra noise when using a large upsampling rate. Next, I will introduce our recent work, which achieve a better performance and also better efficiency. Here, we first revisit the point cloud upsampling task. Essentially, we find it's multiple objective tasks. First, it needs to generate a dense output. Second, you need to ensure a uniform distribution. And sometimes you also need to reduce some noise and also fill in some small holes. Existing framework aim to achieve all these goals by designing one upsampling module. However, it's very hard for such a design to meet all requirements at the same time. So a simple idea for our paper is based on its multiple object nature. It can be easier to take a divide and conquer strategy. We first divide the task into two sub-goals. First, this generator produces a coarse but dense point set which can roughly describe the underlying surface, and then we combine with a spatial refiner to refine the coarse point to better cover the underlying surface for distribution uniformity. This framework is quite general. It's a divide and conquer strategy. It's quite simple but efficient. Compared with previous work, our disentangled design for two advantages. First, our framework assigns no requirement to each sub-networks, and also we allow the two sub-networks to complement with each other, such as is need to a substantial program performance boost. For the architecture design, actually we using for the dense generator, we directly adopt a simplified version from our previous work, and also design a spatial refiner by combining a local refinement and a global refinement to refine the local and the global structure respectively. But when we design the framework, actually after we divide using the divide and conquer strategy, actually no matter how you design this from the detail of this framework, the performance is always better. We also conduct the experiments on both synthetic and the real scan data. Here we first show the comparison result of the upsampling result on the synthetic data. We can see that our point cloud produce more uniform distribution and can preserve the tiny local details. We also show the error map, and the blue means the lower error. We can see that our result when using a larger upsampling rate, because our framework is quite efficient. Here we show the upsampling the result on the real scan data, and we also provide the mesh reconstruction result. Our result can produce a smooth surface and also produce the complete surface. Here is another example. Please note that our framework is directly generalized to real scan data. Okay, here I have talked about my works on upsampling. The first work, PU-GAN, mainly focused on improving the uniformity, and the second work, this PU, utilized a divide and conquer strategy to improving the efficiency. Next, I will talk about my recent work on shape graphics, shape generation on SIGGRAPH this year. In this work, we present SPGAN, which is a new unsupervised generative method. We can directly synthesize 3D shapes from a random vector and also promote controllability for part-aware generation and manipulation. And next, those work in 2D images, such as beam and stair gun, which can already synthesize higher resolution images with fine details. But if you look at the 3D domain, it's totally another story. Although we have achieved some progress in 3D domain, 3D shape generation is still quite challenging due to the large shape variation and high complexity in 3D space. Existing generative model can be roughly divided into autoregressive based, flow-based, and GAN-based. All of them can synthesize different objects from a random latent vector. They often struggle with fine detail, and the generated object tends to be noisy. And it's also hard to find the particle correspondence between the input latent vector and the output part. Therefore, the current method does not enable structure-wise controllability. In this work, we design a new generative method, which not only synthesizes 3D object with finer details, also facilitates structure-aware manipulation. Please notice that our method is unsupervised. It means that we don't need any part annotations. Here we present an overview of our SP GAN. Basically, it includes a generator and a distributor part annotations. And it's quite similar to the previous 3D GAN. But the main difference is the input design. Next, I will talk about why we design like this. Different from a conventional generative method, we design our generator with two decoupled input. First, a global pair in the form of 3D sphere, and a local pair which is a random latent code. During the generation, we attach the sample latent code to each sphere point, and the generator learns to transform the input sphere into a feasible shape. One important insight in this design is that we simplify the complex 3D shape generation task into a global shape modeling and a local structure adjustment. Actually, we turn the generation task into a transformation or deformation task. We turn the 1D to 3D mapping task into a 3D to 3D task, such that we largely alleviate the learning burden and enable a high quality shape generation. Compared with previous method, our generated object contains finer details and less noise. Another important insight is that our new model can implicitly embed a dense correspondence between the input sphere and the output object. Here we categorize the learned dense correspondence of more shapes, and we can find that the correspondence is consistent across different objects, even with those deformed animals. Here I want to talk about a little bit about the design intuition. I take the generation task as a painting task. The generator can be regarded as the painting brush, and the noise vector can be taken as a pigment. When we do the painting, we always have a canvas. Here I design a sphere as the canvas, which can provide a shared working space. After that, we can build the correspondence automatically. But if you don't add this, you can skip that. It's just an interesting thought when I design these tasks. But such dense correspondence can enable a lot of applications and facilitate structure-wise controllability. Firstly, if we just want to modify the latent vector for some point on the sphere and keep others unchanged, we can just only manipulate on the local structure. Let's look at this example. We can only change the chair spec and without touch another area. Further, taking the sphere as a proxy, the dense correspondence can be spread across different objects. Similarly, we can select some part and do the part interpolation between two generated objects. Another application is our learned dense correspondence facilitate a one-shot part to segmentation. Here, we just need to manually segment one instances and directly apply the point-wise label on the other instances, such as all the other shapes are co-segmented without any actual effort. Here we visualize different objects by our framework. As shown, our generated object exhibit fine detail with less noise and also cover different kinds of local and global structures. Our generated object can be also reconstructed as continuous surface. Our result can also conduct the shape interpolation between different objects. We can see that our SPGAN enable a smooth transition from the source to the target object. Because we can learn the dense correspondence, such that we can just interpolate on the associated part. Here we can keep the inner part and conduct interpolation on the other part. Our model can also perform part composition from multiple objects. Here, given several objects, symmetric parts from different objects, we can pack them together to get a new object. Here is a gallery for different generated objects and also different applications. Because our design is quite simple and effectively, such that we got consistently acceptance from our AsiaGraphics reviewers. We also provide an interactive interface. Since our model is rather simple and effective, we can realize the real-time interaction. With our provided interface, its user can select some parts, and we can do the multiplication on the associated part. Okay, in my day, I may talk about my works on the upsampling, which can enhance the raw representation, and also the generation, which can directly generate a diverse object. In the future, may also focus on the generation and the reconstruction. As we all know, the 3D representation contains tons of representation. Here we can show the point cloud meshes, so the grid, and also the implicit functions. But here I may focus on the generation and the reconstruction, and particularly focus on to provide some intuitive, effective, and flexible controllability. My recent work is focused on the mesh generation and the manipulation. The basic idea is we learn a disentangled representation between the topology and the globe shape, such as we can do the interpolation just on the. Here we can keep the globe shape and just do the interpolation on the topology, and on the right we can keep the global. We can keep the topology but do the interpolation on the globe shape. But in the future, I also like to try to provide more fine-grained controllability with the part-wise relation, and maybe also contain some generation based on the user feedback, and also consider the object functionality. Another interesting paper I saw in archive recently is we can do the text-based generation. Here, just look at the left hand. You can see that the object is quite interesting. Maybe some object does not exist. And we can also, on the right, we can also learn to reconstruct some object from the world image, such that we can bring the 2D image to the 3D domain. Besides, I'm also open-minded to bring geometry learning into the biomolecular modeling. And I saw a very inspired paper from CVPR this year. I'm also interested on this domain. I have some collaboration with some researchers, but I'm just an amateur on this domain. I will explore more. Okay, here I just remind my talk today First is upsampling, and the second one is the generation. You can find all the resources on my homepage, and all this works thanks for my amazing collaborators. If for anyone, if you have any further discussion and communication, you can find me using the WeChat or also on the Twitter. I would like to some communication and collaborating with all you guys. And lastly, thanks for the AsiaGraphics committee. I think this is provide a very great opportunity for us. Okay, I think the end. Thanks.
Okay, thank you, Ricky, for the nice talk. So now we are in the Q&A session. So currently there's so I have one question about for all the speakers. So as mentioned by Ricky, so now this learning method are developed for this point cloud data, but there are different ways to represent geometry, right? Mesh, volumetric, or even implicit function. So my question is, so is there any difficulty to extend this method to other geometry representation, especially mesh? Mesh.
I think I can say a bit. I think for mesh, usually when you try to do mesh CNN or things like that, to try to learn the features from meshes, one issue I found out is we found out is that mesh may be too local. And also the other thing is when you have mesh, the sensitivity to the topology as well as the triangulation is also another issue. Actually, mesh is quite challenging on its own, I think.
Okay.
So that's why another issue that is following up because of this is that if you want to connect the mesh features with other point features together somehow, okay, this is also very difficult. So this is a very good question, I think.
Yeah, but are these challenges are possible to be overcome?
I think some people are working towards this direction.
Okay.
I think maybe the graph neural networks may be a good solution to capture the topology in the mesh.
Okay, yeah, that's true. Yeah, because mesh is actually a graph, right? So yeah, that's a natural way to handle mesh.
Yeah, yes.
Also you first.
Sorry. When I designed the SPK, actually, if you look at the detail, is some kinds of lack of the pixel to mesh, because pixel to mesh also contains a sphere, but it's a mesh. So I designed the mesh is some kinds of inspired by the mesh, but mesh-based framework. So in my mind, I think different kinds of, as we all know, we contains tons of representation in 3D. And each representation has their strengths. And for some cases, we can combine them together. Just look at the point detection. I know a lot of work to focus on the voxel and combine the point. They can get a better performance, such that because the voxel is more efficient, the point cloud is more accurate, and combined together, you can get a better performance. So it's quite intuitive. The mesh can be more smooth on the surface, but point is easier to handle. So maybe we can combine them together.
Okay, yeah, that makes sense. So we can use different geometric representation to address a specific problem. Okay, I have another question, which is about this distinctive region detection. So, this very nice work, and you have also, not just demonstrate the technique, not just introduce the technique, but also demonstrate in different applications. So one is shape retrieval, and we know shape retrieval is actually a global shape matching, right? So, both shapes are complete. But is this approach possible to be applied for partial shape matching? For example, for 3D object recognition, right? So it's actually a partial shape matching problem. Actually, it's more challenging, right? Because
of course.
Yeah, so is that possible to address this problem?
Actually, in our shape retrieval application, we focus on the intra-class shape retrieval. It means that there is a data pool and it contains the shapes from the same class. So when we do the ship retrieval, we cannot use the previously commonly used the global feature. Instead, we need to extract the features from these local regions, and we use this one as the guidance to extract to retrieve the ships. So maybe in the future, when we do the part ship retrieval, maybe we can incorporate the part segmentation into existing framework, and maybe we can do a better part-based ship retrieval.
Okay. Yeah. Okay.
Hello, Peng. Yeah, this is Li Gang.
Yeah,
So I happened to listen to all of the talks this evening. So very interesting. Hi, Philip. Yeah. So I have a question for you. So
thank you.
In your talk, you mentioned that in the semantic segmentation, you assign labels to edges instead of vertices or triangles.
Actually,
so,
in addition, sorry.
Okay.
Not just,
But as far as I'm concerned, that traditional methods assign labels to vertices or triangles, not instead of edges, right? So
no. We maybe let me talk a little bit more detail. So actually, we have a label, an object class label for each point in the scene. Okay, this is one label, and actually we can have another label, which means when we connect 2 points, two adjacent or nearby point, we can predict whether these 2 points belongs to the same object. Yes or no. So it's a binary prediction. So that's why we have an edge between points, and then try to make another prediction. Additionally to the class label, we want to predict whether the 2 points have the same label. Because if we have this kind of edge loss, we can increase the interaction between the features.
Okay, I get it. Okay.
Yeah.
Okay. So
sorry, I didn't make it clear. Sorry.
Yeah, so it's okay. Yeah. Okay, I had another question to Xianzi, maybe. Okay. So in the work of rotation invariant features, right? So you adopt 2 attributes. One is global and another is local features. Actually, both of them are man-made or handcrafted features. So in the deep learning, so some guys prefer to use end-to-end deep learning network. So is it possible for you to design a pure end-to-end network for this task instead of using global or local features you mentioned?
Yeah, you're right. Our local and global rotation invariant representations are somehow engineered, so handcrafted. So we manually extract these features from point coordinates as network input. Actually, if we design the framework to be end-to-end, it means that we may need to input the point coordinates into the network, and then let the network to learn the rotation invariant representations. Maybe we can do this, but we cannot ensure the purely rotation invariance. So if we design an end-to-end framework, maybe we can address the rotation invariance to a certain extent, but we cannot ensure a purely rotation invariance. So so it is very difficult to design an end-to-end framework. And we directly input the point coordinates into the network and then let the network to be rotation invariance. It may be much more difficult.
Yeah. But think of point nets. In their work, point net, right? You know, so they learn some local rotation or transformation for each patch or each point. That might be a hint to design some pure end-to-end network. Just my comments. Maybe that might be possible. Okay, so just think about it. Okay. So one comment to the first question, just Peng asked, what's the advantage of meshes over points? So maybe I think different representation are the benefits for different tasks. So I think it's a task dependent problem. I think, yeah, because in some applications, topology, I mean, the connectivity between the points are quite useful. And Xian also mentioned the graph neural network for that. So just a comment. Okay. So overall, good work. Okay, thanks for your talks. Okay.
Okay.
Thank you, Li Gang. Thank you.
Thank you, Li Gang, for the comments. Okay, I have one last question, which is about this shape generation and manipulation. So, okay, so now you can, you can learn the data and generate new shapes, right? So my question is, if in case I want to generate shape that satisfy hard constraints, for example, I want to generate shape that are high field, because the high field shape can be, for example, do the CNC mining, that kind of things. So is that possible to, use this learning method to generate that shapes, with some hard constraints?
Yes, actually, I just saw a paper today. I saw a paper extend of SPGAN to try to compare with a chair. Means that you can make the how to say, their paper is how to make a chair because you can sit on that. This paper is work on this domain. They optimize the human. They can sit on the on a chair. Yes, do this kind of have maybe physical. They can also contain some physical constraints such as the connection, because different parts may be distract, maybe this not connect. This is kind of physical. Actually, you can I saw some paper works on this domain.
Okay, that's nice. Okay, I think that should be all for this talk. And thanks again, the three speakers for the very inspiring talk. And thanks audience for joining this session. Okay, so thank you again, and I will see you later.
See you.
Thank you.
Thank you.
Thank you. Bye-bye.
Bye.
Bye-bye.